right. E.J. Daigle here, Dean of Robotics Manufacturing at Dunwoody College. And today we're going to go through, been dealing with the Scara robot a lot up until this point in the course. And at this point, we're going to move into Epson's 6-axis line of robots. All right. So a couple of things on the 6-axis robot as we compare this to the Scara robot. The Scara robot primarily is a pick-and-place robot, which means it's really good at precision work, high-speed work, but really just up, down, up, down, up, down. The Scara robot tends to work best as long as the Z-plane is flat and we're not trying to get under something or at an angle or something like that. When it comes to the 6-axis robot, we can get into a lot tighter places and deal with surfaces that are at angles to the Z-plane. So working vertically, working underneath something, working at an angle, very, very handy. And you'll notice we've got a lot of joints available to us. The joint of the waist actually allows us to kind of move in this direction around the waist. We then have a shoulder that really kind of tips out this way. You can kind of see it kind of going up and out this way and allows us to kind of move like the arms are like your shoulder to your arm. The elbow, which you'll see right here, this is kind of the elbow on here. So we've got J1, J2, J3. And it's interesting as you get closer and closer to the end of arm tool, you have more joints more tightly packed together. So when you get to joint 4, we get what's called arm rotation. So this Epson actually can rotate around and down, so the Epson can pretty much flip all the way upside down, rotating that arm around. And then the wrist pitch is what you see going on right here, where this end of arm tool can be sticking like this, or can be sticking like this, or can be sticking like this, and we can pitch it up, we can pitch it down, whatever needs to be. But then we also get, let me delete some of that stuff here real quick, just make some room here. So when you get to J4, J5, J6, they're all very out close to that end of arm tool, right? So you've got, essentially J4, J5, and J6. They're all right out by the edge of the end of arm tool. What J6 does is it actually allows this thing to rotate around like this, versus this being kind of my axis of movement for the wrist pitch, and then this is actually that faceplate's ability to rotate around and put into different positions. So what you can see is we can definitely get into some strange, precarious places and do some cool stuff, whether it's to weld something, assemble something, handle some material, whatever that might be. All right, before we get too detailed, I did want to go over, and this is applicable to what we do with all of robotics in general, but I do want to at least talk a little bit about it. It comes up at when we start talking about 6-axis. How does a robot know where it's at? That's really important, right? If I need to go to this location and pick up a part, then I need to know where I'm starting and how I'm going to go about getting there. Well, each one of those axes that we were talking about is run by what we call a servo motor. So in here there's a motor, I'll call it M. And then there's a motor shaft that goes through there that actually turns this. But on the other end of that motor shaft, there's something called an encoder. So each one of those axes has a motor, an encoder, and it has a shaft that's actually hooked up to the gears to do the mechanical work. Well, the beauty of that encoder is the encoder that's hooked up to that shaft has what we call an encoder disc on it. And so this is the cool part. It's like having a measuring tape. It's what it's essentially like. Imagine I want to know, I want to walk 20 feet. If I have a 20-foot measuring tape, I can do that very, very accurately, right? Versus if I just say I'm going to walk 20 feet and kind of guess where 20 feet is, right? So that's how this does it. It basically has a measuring tape. So imagine this is the motor shaft, and down here maybe is the motor, and maybe this is connected on the other side to the actual movement that we're going to move. But as that shaft turns, it's also turning this optical disc, this rotary disc. And it can be made of a lot of different things. It's usually going to be made of a glass, and it has shiny and opaque surfaces. The one that we're seeing right here is a little bit different setup. It's a little bit simpler. Basically, this is a metal disc, and it's got holes in this metal disc. And what we do is we have an LED right here, and that LED is going to shine a light. And every time the light passes through one of those holes, a photocell down here is going to send a signal. So I'm going to get these little square wave signals every time the light shines through. And they're just like pulses, kind of like Morse code almost. And I just count the number of pulses, and if I get 90 degrees worth of pulses, then I know I've moved that motor shaft 90 degrees. If I get 180 degrees worth of pulses, then I know I moved that motor shaft 180 degrees. So I can equate this to position, I can equate this to RPMs, I can acceleration, deceleration. I can work with a lot of different things to determine movement using an optical encoder. The reason why they call it optical is because we're looking for light. And in some cases, we bounce light off of this disc, and we use shiny or white and black. Black would absorb the light and white would reflect it. There's lots of different ways, but it's always going to be some sort of emitter, some sort of light being emitted, and some sort of detector measuring it on the other end. I will note for you here, these are common everywhere. So whether you're working with robots or 3D printers or CNC machines, if you ever hear that term servo motor, you'll know that they're talking about a DC motor that has some sort of encoder hooked up to it that's going to measure the amount of movement. Now there are other types too. We have things like stepper motors that each step is a significant, a certain degree of movement. But servos, steppers, I mean, what they all give us is they give us accuracy. They give us accurate movement, whether it's in a 3D printer or a robot. So I always like to show this with an example, and I know there's one on your homework too, so it's good to do an example right now. So here's a question. Suppose the attached encoder, or the attached encoder, or I guess it's attached to this slide. The attached encoder was attached to a motor shaft. At what RPM is the shaft rotating if the encoder count is 600 pulses in 5 seconds? Well, as soon as I hear the word RPM, I'm thinking, well, first off, I want to know how many pulses are in a minute. So I'm going to, right off the bat, take 600, and I'm going to multiply that by 12. You might say, well, why did you multiply that by 12? Well, the reason why is because 12 times 5 would equal 60 seconds, right? So I'm going to take 600 and I'm going to multiply that by 12, and that gives me 7,200 pulses per minute. Now that's not RPMs, that's pulses per minute. So that means this wheel has gone around and this little photo detector has detected 7,200 of these little pulses in a minute. That thing's screaming, right? It's moving pretty quick. Well, maybe it is, maybe it isn't. If there's 500 pulses on a revolution, then it's probably not moving that fast, right? However, we can see on this one, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 pulses per revolution. Okay, so 16 pulses per revolution. So that means if I've got 7,200 pulses per minute and I've got 16 pulses per revolution, then I can do the math and divide that by 16, and I get 450 RPMs, I think is what I should have there. 450 revolutions per minute. And what I like about the math, if you ever work with like physicists or anything like that, they always like to include the units. So the pp go away, and all I have left is revolutions in a minute, which we call revolutions per minute. All right, now that's all fine and good. But now let's suppose that the same encoder was tied to J4 on a Scara robot. So if you remember where J4 was on a Scara robot, our Scara robot looks kind of like this, right? Kind of goes out and out again, and then we have this little head, and there's some little thing that goes up and down in Z, right? Goes Z plus and Z minus. This would be it's the worst drawing of a Scara robot ever. But that J4 is the up and down movement of that shaft, right, on the Scara robot. So now we say, okay, that same encoder is tied to J4 on a Scara robot. If 150 pulses equals 1 inch of travel, then how far has the Z-axis moved for 600 pulses? Well, I don't think this one's that bad, right? So 150 pulses, I don't have to go, at least I don't have to go count the number of pulses, equals 1 inch of travel. So I just know that, right? And I know I have 600 pulses, right? Divided by, and I could do the same thing, right? 600 pulses per inch divided by 150 pulses. Oh, excuse me. 600 pulses divided by 150 pulses per inch. That's what I was looking for. Let me erase that. That's the messiest thing in the world right there. Let's get the eraser out there real quick. There we go. We can clean this guy up a little bit here. Go back to my pen. All right, let's type this up again. We got 600 pulses. And we don't know how many inches, but we do know that 150 pulses per inch. All right, I'm trying to play physicist here and keep all my units straight. Well, 600 divided by 150, I believe, is going to give us 4. The pulses and pulses cancel out, so we get 4 inches of travel. And we probably didn't need to show the math there. A good idea to do it just to make sure that we're making sense. But we know 150 pulses is 1 inch. It would make sense 4 times the amount of pulses would be 4 times the amount of Z travel. All right, now here's where it's going to get interesting, and I'm going to show you some of this here in a demo in just a few minutes. I actually should probably get my software booted up while we can take the software a second to open here. So let's open up our Epson software and let that kind of start going while I'm waiting here. Epson, so that's booting up. Let that boot up in the background, I hope, and it might come into the foreground. That's okay. All right, so first off, before we drill into the demo on this, one of the things I want you to note is when we get into 6-axis motion, we're going to talk a little bit about the difference between joint and world. And when you were moving the Scara robot around and you were positioning it around, that was a little bit tricky, a little bit difficult, right? We're gonna encompass the same thing now, right? But now we're gonna do it with 6 independent axes. And if you had to move J1 a little bit, J2 a little bit, J3 a little bit, J4 a little bit, J5 a little bit, J6 a little bit, what you're gonna discover, it's gonna be painful to get that robot to where you want it. So we actually have 2 modes of operation. We have something called joint mode. And in joint mode, we can move each joint independently of each other, kind of like we did in the Scara robot. I can grab joint 1 and move it around, grab joint 2 and move it around. But I can also, from what's called the teach pendant, I can drive J1 in the positive and the negative direction. You can kind of see it's trying to tell you which way those go, and they're actually labeled on the robot as well. I can drive J2, J3, J4, J5, J6. By just clicking on these buttons, I can do that. Now realize what's going to happen as you do that. If I'm moving J1, all that's going to do is it's just going to move this thing around, right? And if I'm trying to line up to something, and keep my end of arm tool straight, like a move function in the Scara, going to be hard to do, right? Because I'm only moving one joint. We know we'd have to move multiple joints to keep that end of arm tool, in a straight line or something like that. So they've developed something called world mode. This is a really, really handy tool. And it's as simple as changing the mode here from joint to world. Now what's interesting when you do that is instead of seeing J1, J2, J3, J4, J5, J6, now you see a Cartesian coordinate system, X, Y, and Z. You also see U, V, and W. But the beauty of this is now I can say, okay, well, I have, X here, let's say, right? And I have Y here. I can travel along X in the positive direction or along X in the negative direction and keep everything in line with what I'm doing. This is going to make your programming so much easier. And you're not going to appreciate it by just looking at this slide. I'm going to have to show you a demo here in a minute, and I think you'll really, really appreciate this. All right. I want to talk a little bit about a digital twin. So what we're going to build today is we're going to build a model, essentially a model of some process. So a digital twin refers to a replica and a model, a simulation, an emulation of a potential of something with a physical asset, a process, a manufacturing process. Could be a system, could be traffic patterns. But the beauty of creating a digital model is we can simulate and make changes and commission and try different things without investing all of the infrastructure money to make that happen. So I love this slide because you see maybe this is, I don't know, this is an oil rig, I guess. And we want to determine, is this going to work? What's this pump's capacity? What's this tank's capacity? What's this crane's capacity? We might even put some forces on this thing and, and see how much it can withstand. And the more data we have built into the model, the more we can test it. So I pulled this from the most recent, oh God, what's the name of the magazine? The ISA has a magazine in Tech, I think it's called. And they actually had an article on digital twins this month. Digital twins are used to simulate manufacturing processes to ensure processes are capable prior to making large capital investments. So you can think about what we're doing with a robot right now. If somebody gave you a couple pieces of metal and said, hey, can you train this robot to weld this? Yes. Well, what if we added this? Can it do this? Okay, let me try it in the model and see. And then if you can prove it in the model, then it's that much easier to spend the $30,000, $40,000, or $100,000 to actually build it to scale and actually make sure it's going to work. All right. So, I did bring something in here. This is kind of cool. This is what they call a teach pendant. So everything you guys have done up till now with the Scara robot has really been physically moving the robot around to teach the points. But in most cases, we're going to actually move the points, X and, and you'll see these are actually labeled. You can't quite see it here. But this button says X plus and this button says X minus, but then it also says J1 and J1. So if I'm in the Cartesian coordinate system or the world system, I'm going to go off of X. And if I'm in the joint system, I'm going to go off of J or J1. And then I have J2, J3, and I'm going to have Y, Z, and U, V, W, and so on and so forth. But this is in the real world. This is what we use a lot of times when we're programming the robot. I may not have to go get a computer. I can grab a teach pendant, program in a couple of points, and get it working. All right, so what we're going to do today is we're going to import a CAD model into our simulation. We're going to put that CAD model where we think we want to put it. We'll move it, rotate it, whatever we need to do. We're going to select an end-of-arm tool, and then we're going to demonstrate programming a point from the teach pendant, and we'll probably move it around physically as well as we're doing some of this. We'll demonstrate joint mode, and we'll demonstrate world mode. So we're going to demonstrate the different modes of motion that we can use. So with that, I'm going to discard my ink annotations here, and I'm going to move my little pad here, get it out of the way, and then grab my mouse here, and hopefully we've got our Epson software open right now, which it looks like we do. And I'm going to bring up the simulator. I guess one thing I need to do before I do anything is get you guys to grab a 6-axis robot. I didn't have that on my list of things that we need to do. And I can see I've already got a 6-axis robot in here, and I can almost guarantee you guys don't. And I also have CAD in here that I can almost guarantee that you guys don't have as well. So I don't know why, if I can get rid of that CAD, I go into the 2D layout. I want to start with a blank template because this is where you guys are going to start as well. All right. So the first thing you're going to have to do is when you click on robot, you're going to have to go to change robot. So you click here to change the robot. And when you do that, you're going to change from a Scara, which is where you guys are at right now, to a 6-axis. And I'm actually picking the C3. And then which one did I pick here? I picked the A600S, the first one on the list. So I'm just changing my robot to a C3 A600S. I'm going to cancel out because when you do that, I will warn you, it'll ask if you want to save your Scara stuff. Sure, you can save it. And then it's going to restart the whole program. So I'm not going to do that right now because I've already got mine up and running. But it will actually restart the whole program because it's actually simulating restarting the controller altogether. So basically setting up the software, for a new type of robot. All right, when you go into Canvas this week, one of the things that you're going to notice when you go into the lab for this week is that I've got a couple of files in here. I've got the frame stand, which is a step file. It's basically just a CAD model. And I've got the G10 tool, which is also a step file, which again is just a CAD model. These two files you're going to have to download and put them on your computer somewhere. The reason being is what you're going to do, first and foremost, before you do anything else, is I want you to go into CAD. So right up here where it says CAD, wherever you've saved those two files to, you're going to browse to them. And I know I've got mine I've got a folder called Object Samples. And I'm going to grab the frame stand.step and open it up. And then hit open. And that's going to bring that model into your simulation. So you can see it's going to think for a little bit. It's going to say, oh, there's a step file. And then it's going to also do something which I kind of hate, but it does it. It's going to bring it in based upon kind of where the Z-plane is 0. So depending on who modeled that file, it could come in like it's looking like half of it's underwater right now, which isn't the case. But what I will tell you is it's actually fairly simple to do. What you can do is you can move the object by clicking Move Object and then clicking on the object, and you'll see this little red line will show up, and you can bring him up. Let's try to get him up to the surface maybe. And then you can also rotate him with this one right here. So just like we're jogging the robot, we can also kind of jog the table here. This is a little bit trickier now. Let me see here. I can stand him up. Okay, now he's really in a precarious position. He's like in midair, right? How do I fix that? Well, I go back to the move and I grab that table and I drag him back down to the surface, right? And I think somewhere, and I'm not going to get real hypercritical. If you feel like you got it in the right spot, I'm going to call it good, right? It looks like he might be a little below the surface, but we're going to call him good for right now. The other thing you can do then is you can also move him maybe a little closer to the robot if you want. So I could say, okay, I want to move a little bit more. I'll click on Move, and I'll click here, and I can go on this green line, kind of slide him across, and I'm just going to go like right here for now. Whatever's most convenient, we'll call that good. He's kind of, he might be a little close to the robot. Let's maybe move him a little bit out too. So I'll click here and I'll go out a little bit as well. Close enough. I'm going to just call it good. You're going to have to figure out what that position is and where we're going to put that guy to work on him. All right. But I think we've got a good we've got a pretty good start there. Now we can also do that with the robot, right? I can click here on object orientation, and I can actually grab an axis on the robot and I can twist it around, right? And I can also drive this guy down and do all that stuff. So just like we did with the Scara, but now we have 6 axes of rotation, so we've got a lot of movement that we're capable of, right? All right, so we've got our CAD model in there. We're feeling pretty good about that guy. The next thing I want to do is I want to add an end of arm tool. So the other thing that you'll see in Canvas this week is you'll see the G10 tool. It's just a tool. What we're going to do this week is we're going to simulate welding this table up. So we'll pretend maybe it's tacked up, maybe it's fitted up, maybe it's fixtured up. We're not going to get crazy on the model itself, but we are going to hit a button there. We are going to pretend we're putting some welds, right? So what I'm going to do now is I need something that looks like a welding torch. So I'm going to go into the robot right here, and then I'm going to go up here, and I have my CAD model that I brought in, but I also have a hand. I'm going to go into hand, and I saved that G10 in a folder called hand samples, G10, and it's called a G10, well, it should just be called G10 tool.step. Mine's saved a little differently. I made yours a little simpler though. So it'll be G10 tool.step. And now when this comes in, you're going to see it comes in like a little, I don't know, what do we call it? We'll call it a welding torch is what we're going to call it. But I'm not a real big fan because it's coming in at kind of a 90-degree angle, isn't it? I wonder if I can I rotate it? Maybe. Let's do this. I don't know if I can rotate it. I do know another way to rotate it though, so let's not worry about that. Another way to rotate it is if you actually go into the hand right here in the layout objects, you've got a hand now. Now if you scroll down a little bit, you can actually do a rotation in here. And just got to look at which axis you're looking at, right? So where do I want to rotate? Well, I want to rotate out, right? I want to come out like it's a welding torch sticking straight out on Z here. So I feel like I got to rotate about the x-axis. So let's try 90 degrees in X. Oh, that's perfect. So now what you can see is it's almost like I got a little welding torch on the end of there. It's not a welding torch. I don't even know what tool this is. It looks like it's a little suction cup or a touch probe or something. But what we're going to call this is we're going to call it a welding torch. We'll pretend that that's an electrode coming out of a MIG torch, whatever it might be. We're just going to pretend for today's sake. So now we've got something that we think we can weld with. We're like, okay, I can weld with this. This is going to work for me. And here's where it gets funky again. What I'm going to have you guys do is you're going to do a bunch of welds. You're going to weld the bottom of the table here to the top of this pole. You're going to weld the pole. It always screws me up trying to get this right where I want, down to this base piece here. And then I'm going to put a weld here and a weld here. So that's what you're going to have to do for today's lab. But for right now, we're not going to do that. We're going to make it a little simpler, and we're just going to go do something with this just so you guys get an idea how this works. And you may decide that, boy, I really need to move this table out, right? I'm going to click on the table and I'm going to move him out a little bit because he's too darn close to where I want to be, and I'll move him out a little bit. And I'm fine with that. All right, so now what we're going to do is we're going to go ahead and jog this robot to a location that I think is close. So I'm just going to do something. I don't know where I'll do it. I don't want to do the exact lab because I want you guys to do the lab, right? So what I'm going to do is I'm going to bring my robot down a little bit, and I'll bring this back out a little bit, and we'll drag this down a little bit as well. And maybe we can get close now. Feeling pretty good. Maybe I'll just cut along this edge here or something like that. I don't know if my arm's going to fit under there. I think he will. So I'll go down a little bit more. Maybe I can get out a little bit even, huh? Get on this edge here. Oh, I kind of like that. That's pretty good. Bring it down. Oop. And if we crash, that's okay, right? We can crash. There's no problems there. We just got to reset the crash with this little reset collision. And can I come down? Sure. I feel like I want to rotate over a little bit, try to get where I want to get. All right. Now what you'll notice is what we've been operating in right now is what I would call the joint mode, right? Actually, I'll go right here. Some of you folks that are really good at CAD are going to be a lot better at this than I am. All right, but let's just go there for now and call it good. I'll reset my collision there. All right, let's say that I want to just draw a line along this edge, right? If that's all I want to do is just draw a line along this edge right here. Boom, boom, boom. Go in that direction. So as you're looking at the thing, I'm going to start here and I'm going to kind of go along this edge. Now, that's going to be painful to do, to program that point in there, right? I still have code left from my previous stuff. This is a 6-axis demo. But let's say I just want to go between 2 points. So I'll go to point 0 and I'll be fine. And then when I get from that point, I want to go move point 1. So I'm actually using the exact same code as what I've done with with my previous scare examples. But how I'm getting the points is going to be a little bit different. And then points, do I have some? I got some. I'm going to delete them all out for now. It's just an old program. And then I'll go back to my simulation. And if I want to just call this a, let's say I want to call this point 0, right? I could do that. I could go ahead and say, you know what? We're going to, let's see here. We're going to call this point 0. So teach a point, point 0, local, done. Now, what we maybe have done in the past is maybe we would zoom in, right? And we would try to go all the way across there. Here's where I'm going to change it up a little bit for you. What I want you guys to do is you go to Tools and you go to Robot Manager. And when you go into your Robot Manager, there's a couple of things that are important here. If you ever get an error, not a crash error, but like an acceleration error or something like that, you can always reset that error here and you can turn your motors on here, okay? If you ever get an error, you reset here, you turn your motors on. But what the real reason why we're coming in here is I want to go to Jog and Teach. You'll see I can be in joint mode, and if I'm in joint mode, I can move those individual joints little by little by little, right? And I can actually pull this up to the side, and I could actually watch what's going to happen over here, couldn't I? I can make this maybe pull this way a little bit. I don't need that much of that menu. I want more of this menu. And we'll pull them over a little bit so we can just see them. So let's say, you know, I want to move J1 a little bit. You can see how J1 moves just a little bit, right? But I'm only moving J1. And here I'm only moving J2, which might be handy, right? I can get a lot finer control with this thing by moving the joints like this. But where it comes in real handy, and I'll move J1 maybe back a little bit this way. But where it comes in really handy is once I have that first point, let me reteach that point again. So I'm going to call this P0 again. I'm going to teach it. Yep, reteach. But now what I'm going to do is I'm going to change it up a little bit. Instead of running in joint mode, I'm going to run in world mode. You might say, well, why do I want to run in world mode? Well, the reason why is because I know that this thing is essentially on the Cartesian coordinate system, right? I've got, you know, X, Y, and Z here, right? So if I move in Y, look what it does. It kind of runs along this axis, doesn't it? All right. But if I move in X, and I should probably reteach that point now that I've taken myself out of the Y. So I'm going to reteach point 0 again because I just changed my Y. But if I want to move, so that was my Y. If I want to move my X now, I can move in my X this way, and I'm just going to slide all the way across this thing, boom, 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 until I'm pretty happy as to where I'm at. So if I was triggering a weld, let's say, I could go all the way across here and just keep going and going and going. And I can change my speed if I'm going kind of slow, right? That doesn't affect how fast I go here, of course, but and what you'll notice, there are other things changing as I do this, right? My Y is staying the same, but as I move this X plus, you see my Z may change a little bit. Some of the U and V and things are changing a little bit too. And so now when I go to teach that next point, I can hit teach for P1. And now what should happen when I go to run this, I go to the run window, and I go to start, ready to start. Oop, let's get out of there. There we go. Ooh, I just crashed it. And I might say, well, why did I crash it? Well, I can tell you almost for sure why I crashed it. It was fine going the one direction. Oh, I'm surprised it didn't crash again. That's kind of, yeah. I'm pretty sure what we're seeing happen there is we're seeing the, zoom out a little bit. Thinking the top of my robot there is just a little bit too tight. So let's hit the, yeah, this piece right here is just a little bit too tight to the robot there. So I would have to maybe, I could even reteach these, right? I could say, you know what? Those points are garbage. Let me get out of there. It's my robot manager. Those points are junk. I'm going to delete those out. And I want to get back in there a little bit differently now. So I'm going to go back into my, let's see here. I don't need that, but I do need this, I think. Nope. Well, I can find it by going again to Tools, Robot Manager. And, oh, there we go. I'm on it. It's the same with my points. I'm going to go to Jog and Teach. I'm going to go back into my Joint tool. And what I'm going to do to try to fix this is I'm going to, let's see, reset the fault. And we got to think J1, J2, is it J2 that we can pull in? Maybe a little bit. J3 could come this way maybe a little bit. J4 I don't care about as much. But J5 I think I could angle. You can see how J5 is moving right now. You can kind of see how I get nice and accurate. Now if that's moving too slow, of course I can always come over here and hit this, right? And grab J5 and move it in. Now, oh, I love this error. Okay, this is an error that's very, very important. If you get an acceleration error like this, this is where you need to go back into your controller and go into the control panel, and the motors are off, so you need to reset everything and go motor on. What can happen is if you start moving one thing a little too fast, and sometimes the joints are a little bit out of sync with each other, you may not always get the result that you want, and it'll give you an error. So I'm going to go back to just doing it kind of slow with J5 here and kind of get that to where the point of the tool is further out. Yeah, about like that. So now I'm not going to crash anymore. I feel a little bit better about that. And now I'll go ahead and I'll program that first point. I maybe will move around a little bit so I can see where I'm at. And I don't know, I could move J1, but I'm just going to do it real quick here just so you guys get the idea. So I'll program in a point for 0.0 again. Yep. And then I'm going to go to world. Okay, joint is how I got to where I think I needed to be. Now remember, where are we going? We're not going on Y, we're going on X, right? And we're going X positive. So I'm going to go this way. I kind of want to see how it's working. So I'm going to come in a little bit and down a little bit. All right. I'm going to go in the right direction. That's the question you always got to ask yourself, right? So you can see I'm definitely going the right direction now. Now I may at this point decide to do another point just to see what happens. Teach that point in there. I'll go to my run window. Hit start. Ready to start. We'll see what happens. This one's kind of funky. Kept my tool in that same orientation. It's just kind of rotating J3. But what you can notice here is you can see that it's actually maintaining a nice straight line there. So the move instruction combined with the movement that I'm making right there is keeping that thing in a nice straight line as it's going forward. All right, so hopefully that kind of makes sense for what we're doing. You know, as you look at this table, I want to show you guys the lab first probably, just to give you guys an idea of what's going on here. 6-axis lab. All right, so on the lab for this week, describe the difference between joint and world. That should be pretty easy. Individual joint movement versus moving along Cartesian coordinates, X, Y's, and Z's. All right. The encoder shown below, if it's 200 pulses equals 3.25 millimeters of travel, how far did J1 travel for 1,250 pulses? Yeah, people hate this question when I ask it because, yes, you have to count the slots. So this is a little LED with an emitter and a receiver. And this wheel would spin around, and this would just it would spin around with this emitter receiver kind of sandwiching it to be able to read the slots as they come by. What is a digital twin? We talked about that. Why is it valuable? And then this is where it gets tricky. All right, so what you're going to do is you're going to import that frame stand into your simulation, which we just did. So I think step 1 is probably done if you've been following along. Step 2 is we're going to select the appropriate end of arm tool, G10 tool. That's going to simulate a welding torch. Step 3, we're going to program the robot to weld along the joint between the tabletop and upright. That's up here. Between the tabletop and upright. And I want you to hit at least 2 sides. If somebody can get it to do all around, that's incredible. I don't think anybody's going to, but I would hit this side and this side. So you basically go in there with your torch and you draw a line there and you draw a line there. The goal is to keep that torch at an angle coming into that joint and just pull it across there. It doesn't have to touch the joint. Get it close and get it to go along that seam is all we're looking for. Then we're going to program the robot to weld both legs across, to weld the joint between the upright and the base. So that's going to be step 4, and you can see where step 4 is pointing. So between the upright and the base, this is the upright, this is the base piece, right? And so what you need to do there is you must hit 3 sides. So my recommendation there, you can see I was actually doing this job earlier, is I do this side, I do the front that's closest to the robot, and then I do that side. And you should be able to get all around there, the 3 sides. I don't think you'll be able to get back here. I've tried, and it's possible depending on how your shape is oriented, but it's very, very difficult. All right, then step 5, program the robot to weld both legs across the top. Weld only needs to go across the top of this joint. So in this particular case, it's going to go across here, and it's going to go across here, just connecting these stabilizers to this cross beam. So a little joint here, a little joint there, and then you're basically done. Is this hard? Yeah, this is hard, especially hard in a simulated environment than it would be if we were doing this really in the lab. So then you'll comment your code, ensure the code meets the steps above. Save the following files and email them to your instructor. So a Word file, a Notepad file, an Excel file is what I want. So your point data will come in the Excel file, the Notepad file with your program code, and then your Word file. And I will ask you to do one thing for me, and that is to orient the workpiece similar to what I have done. Meaning I want the legs to be kind of facing the robot, and the upright and the table across like this. And you might say, well, why is that important? The only reason that's important is because when you send me that group of robot points, I don't actually get necessarily exactly where your table is positioned. But once I see you make that first seam, I can very easily orient my table to where that first seam is, and then everything else will be in place. So that's how I go about grading it, to make sure that you are actually putting the seams where they belong, and so on and so forth. So with that, that will conclude this lesson on Epson 6-axis robots. I hope that makes sense for you, and I hope that you guys reach out to me with any questions or concerns that you may have when working with the 6-axis robot. Thank you.